Hello, everyone. Welcome to the online seminar of TÜBİTAK Research Institute for Fundamental Sciences for national and international audiences. I have the honor of introducing our speaker, Professor Barry Sanders from the University of Calgary in Canada, a distinguished physicist and world-class expert in the field of quantum science and technology. Professor Barry Sanders is especially well known for seminal contribution to theory of quantum limited measurement, highly non-classical light, practical quantum cryptography, and optical implementation of quantum information tasks. Today, he is going to talk all about security for quantum network. The talk is part of our quantum science and technology seminar series. At the end of the talk, we will have a session for questions, which can be asked by sending a message through chat button of the Zoom platform or just by raising hand. Professor Barry Sanders is director of the Institute for Quantum Science and Technology at the University of Calgary, lead investigator of the Alberta Major Innovation Fund project on quantum technologies, a distinguished chair professor at the University of Science and Technology in China, and a Vajra visiting faculty member of the Raman Research Institute in India. Barry Sanders received his Bachelor of Science degree from the University of Calgary in 1984 and the Diploma of Imperial College London, supervised by Professor Sir Thomas W.B. Keppel in 1985. At the Imperial College, he's also completed a PhD in 1987. Later on, his postdoctoral research was at the Australian National University, the University of Queensland, and the University of Waikato. And finally, he became a full professor at the University of Calgary. Professor Barry Sanders has many awards. In particular, he's a fellow of the Institute of Physics in United Kingdom, the Optical Society of America, the Australian Institute of Physics, the American Physical Society, and the Royal Society of Canada, and so on. In 2016, he was also awarded the Imperial College London Doctor of Science degree. At this point, I want to hand over the word to Barry Sanders to begin his talk. Barry, thank you once again for accepting our invitation for this seminar. And please.
Thank you very much, Alikram. It's a great pleasure to be here. You can hear me okay, right? Everything's good?
Yeah,
great. Okay.
It's good.
Right, so yeah, it's a great pleasure to be here. I would really have liked to visit in person, but these days we have a pandemic and it's hard to travel. So instead I've gone to the moon, as you can see. There's no pandemic out here, no air, no bugs. So I'd like to talk to you about security for quantum networks. It's actually the first time I'm speaking about this topic. So what I'm going to talk to you about is very fresh. My student Shalini Karavade and I have worked hard to prepare for this session. And she does 99% of the work I get to present. So at some point, I'm going to pass over to her so she can give a couple of slides and then she'll pass back to me. And that way you get to know the student who's really behind the work. Yes, I work at the University of Calgary, and the project behind this presentation is supported by the Alberta government. So Alberta is a province of Canada, and our government is very interested in applications of quantum. And so making quantum networks secure is a topic that is important, not only in science, but also beyond to society and economics. So I'm going to talk to you about stuff. I know this is a basic science institute. What I'm going to talk about has a lot of basic science behind it, but I'm showing you the roadmap to the full, to where it becomes important, right to the use cases. Okay. Oops. Okay, this is the breakdown of what we're doing in the talk. I'll introduce various things to you. Then I'll give you a few slides of motivation and pass over to Shalini for a last slide on motivating the work. She'll talk about some background and then pass back to me to continue. We'll talk about our approach to this whole topic, some basic results we have so far, and conclude. You can see I like social media a lot, so there's various ways to find me in the internet. And that's a picture of Calgary. So you can see I'm not actually on the moon, I'm really in Calgary, and that's what Calgary looks like. Okay, I'd like to begin by telling you the aim of our work to make it very clear. There's the science behind it, but the aim is to construct a framework for developing and assessing secure quantum networks. And as I'll show a little bit later, quantum networks are very recently an extremely hot topic. They've been conceived of before, but we're reaching a technological stage in quantum information where quantum networks are now a big topic. We hear a lot about quantum computing these days. Quantum networks are also a very hot topic, perhaps a little less in the news, but the idea is to establish secure quantum communication networks, but there are other applications as well. And we're taking best practice in engineering and using that to inspire us on how to make quantum networks secure. And just to be clear about the background, this picture from Encyclopedia Britannica, 1999, 21 years ago, you can see the computers they're using and the mainframes and even the telephones, that this is a 2-decade-old picture because their technology is not what we have today. But you can see the concept of a network for telecommunication there. We have, you can see a set of users. The users are defined by using the network in various ways, computers, telephones, and then they're connected by links. And these links have to be set up in a way that two or more parties can become a part of the subnetwork so they can communicate with each other. And of course, where quantum is going to come in is we have to consider teleportation, entanglement, coherent transport of qubits, and so on. So somehow this notion of a layer has to be developed to accommodate quantum resources. That's the idea. So that's our aim, to create a framework for doing it. So we're not actually solving all the problems with the quantum network, but we're in a way making a checklist to go through all the aspects of this network to make sure it's done properly. So we're not actually solving all the problems with the quantum network. Oh, I'm hearing myself. Okay. Then these are the claims. So these are the two things that we want to highlight that we've achieved so far. One is that we formulated security requirements, and here in parentheses you see sec. So I'll often write or say sec instead of security. Q is already short for quantum, and then we will explain how we formulate security, bearing in mind the network model. So what is the network architecture? We have to identify the threat models. For example, does the adversary, the enemy, have the capability of entangling with our stuff? Does the enemy have a quantum computer? And so we have to consider all these threat models. And then we're using classical security practices to inspire us on how to tackle the quantum adversary problem. And the second claim that we have is using our framework, we're able to identify what we argue are priority directions for further investigation. So we're looking at a way to identify what are the priority topics that need to be studied in quantum information. And on the right, you can see a picture of the CIA triad. CIA here stands for confidentiality, integrity, and availability. The picture is taken from the web. You can see with that tiny URL where we got the picture, to give due credit to the creator. And in the middle, you see information security. So when we talk about information security, you can see from this diagram, there's integrity. You see the check mark on the document. So the integrity guarantees that it's working properly. Availability means that the network works when you need it to work. That's why the clock is shown. And the confidentiality is that the messages, the transmissions are private and protected. And usually in quantum information, we focus only on the confidentiality aspect and only a subset thereof. But in networks, there's a broader perspective. So integrity and availability are also useful, and these are underexplored yet necessary topics for studies with quantum networks. So this slide is conveying to you that thinking about the CIA triad opens the door to a lot of interesting problems that are as yet underexplored. So in what we're doing, what makes it new and different from the rest of the field is, number one, that we are formulating our network security objectives following the CIA triad model for information security. We could use other models, but the CIA triad is widely adopted and it's a very good starting point. So we use the CIA triad to formulate those objectives. This is a new thing nobody's done. And second, we are incorporating these security mechanisms that are devised through our procedure into network communication protocols. And why is this important? It's because if we're developing quantum networks, they have to be secure. And security has to be defined by what is considered to be secure in networks. So physicists will define security, computer scientists will define in various ways, but ultimately a network has to be secure by the standards of a network. And so this approach we're using aims to guarantee the reliability and efficiency of a quantum network using a realistic framework. And we identify and mitigate the internal and external security risks. So that's the importance of what we're doing. This slide now moves to motivation. So you can see on the top bar which section of the talk we're in. We finished the introduction, we've gone to motivation. And this slide presents some of the papers, recent papers, that convey to you how this is seen to be important. So you don't have to take my word for it. These papers are doing the job as well. On the upper left, this is a paper under 2 years old that appeared in Science. It's by a group in Netherlands, and they're spelling out a vision for a quantum internet. And so they talk about key aspects in creating the quantum internet. They're not focused in this article on security, but rather on the steps to create it. On the upper right, that's an article from Scientific American, which probably you know is a very popular scientific magazine. And the Scientific American article from 2019, so about a year ago, talks about the quantum internet emerging one experiment at a time. So they're conveying the quantum internet is happening. On the lower left, that's an article from the Netherlands, same as the upper left article. And this is a technical article that was presented last year in August, so a year ago, by the group from Netherlands on a link layer protocol for quantum networks. So they're developing the quantum network aspect. They are not so concerned about the security side. On the lower right, in the communications of the ACM, so the ACM is the Association for Computer Machinery, it's a computer science organization, they're talking about cybersecurity in the quantum era. And so these articles are showing you that it's a very current and hot topic to deal with the quantum internet and quantum networks. But I'm also conveying to you that the considerations of security and the considerations of network are quite separate at this time. And we're going to argue that that's not a good approach, that they need to be co-developed. And then why is it important to get everything right? Well, these 4 use cases that I'm telling you about are conveying to you the importance. So these use cases give you examples where a quantum network might be important. One is clock synchronization. So we know that we have atomic clocks. These are the standard for keeping time, and they're extremely precise, within a second accuracy over the age of the universe, so they're amazing. We still want them to get better. And in principle, if we can make atomic clocks operate beyond the standard limit using resources like entanglement, and we connect atomic clocks together, we could have a network of quantum clocks that are synchronized, and that's what the upper picture on the right is showing you. The references, these references are using short DOI. So the DOI is the digital object identifier. If you go to doi.org and type these short codes in, you can find the articles these pictures came from. But the clock synchronization would be a way of using satellites to connect these clocks together, and these satellites would be responsible for entanglement generation and sharing it. But we could be relying on this clock network, and an adversary could sabotage it. And so preventing sabotage is important, and this needs to be part of the network design for entangling quantum clocks together. Quantum sensing, we can have quantum sensing networks, let's say for mining, and we need to make sure that data corruption doesn't happen. And now on the lower right, you probably know about China launched a satellite that is now capable of intercontinental communication. And we have to worry about a man-in-the-middle attack on trusted relays, because on the ground, to connect to the ground stations, there are relays that carry photons from point to point. Those relays could be subject to man-in-the-middle attacks. We have to be concerned about that. That's another aspect of quantum network security. And the final use case that we present here is delegated quantum computation. This is the idea of having, say, distributed multiple small quantum computers and being able to delegate tasks to other quantum computers. A denial of service attack is possible. So we can imagine the quantum cloud, and denial of service attacks can occur. We have to be able to develop our security so denial of service attacks are not a big problem for a quantum cloud. So these are just 4 examples. We can think of more. With that, I'm going to turn over to Shalini to articulate the warning that motivates our work and connects the topics of quantum networks and security together. So Shalini is my PhD student in Calgary, and she'll speak for the next 2 slides.
Thank you, Barry. The Network Working Group of the Internet Engineering Task Force, in their publication RFC 3631, provides us with the following warning. Finally, security mechanisms are not magic pixie dust that can be sprinkled over completed protocols. It is rare that security can be bolted on later. Good designs, that is, secure and clean and efficient designs, occur when the security mechanisms are crafted along with the protocol. Motivated by this warning, our entire approach to quantum network considers security right at the outset of the analysis. I now move on to the background essential to our work by explaining the basics of classical network security. In the opening slide, Barry had described the structure of a general telecommunication network. Going into the details, the functions of the various components of a network and their interconnections are described using what is called as a network architecture. Classical networks commonly use what is known as a layered architecture. The layered architecture is shown in the diagram to the right of the slide. A layered architecture essentially divides the functions of a node in the a node connected to the network into a stack of layers. A node could be anything, such as a computer or a telephone or a router or any such device that is connected to a network, and it is capable of receiving and transmitting data. So as you can see in the diagram, the lower layers of a network stack directly deal with the physical transmission of the data through the communication channel that connects the nodes with each other. Whereas the higher levels of the network stack generally utilize the services that are provided by these lower layers in order to carry out more sophisticated tasks, such as file transfer or distributed computing. The right of the diagram on the slide describes the layers in the OSI model. The OSI model, Open Systems Interconnection Model, is a conceptual model that is used to standardize the functions of a classical network. As you can see in the diagram, the lowest layer of the OSI model, the lowest of the 7 layers, it is known as the physical layer. The physical layer is responsible for transmitting data in the form of bit streams from one node to another through the communication channel, which could be a fiber optical cable or generally the free space. It could be anything. Whereas the data link layer that sits on top of the physical layer controls the physical layer in order to ensure reliable data delivery from one node to another. The network layer that comes on top of the data link layer is a rather important layer in the OSI model. The network layer carries out routing related tasks when the 2 communicating nodes are sitting in 2 different networks and do not have a direct connection between them. Yet another important layer in the OSI model is the transport layer that comes above the network layer. The transport layer is responsible for handling the complete transmission of messages from one node to another, not just in the form of bit streams as done by the physical layer. The transport layer is also responsible for reinitiating the transmission in case any error happens to the whole process. Higher layers that come above the transport layer, that are the session, presentation, and application layers in the OSI model, are in general responsible for generating and receiving data for various applications, encrypting and compressing the data as required, and maintaining communication sessions between the communicating nodes. Let me note that the OSI model is not implemented in practice. It is only a conceptual model. However, the internet, the classical internet that we have around us, uses a very similar architecture. It is called the TCP/IP model. The TCP/IP model has a 5-layered architecture, and the comparison of its structure with the OSI model is shown on the right side of the diagram. And we can see that the layers generally compare, but the TCP/IP model have far fewer layers than the OSI model, but their functions are roughly similar. Okay, and I also note that in practice, there exists unlayered network architectures for describing the functions of a classical network. An example is a monolithic network architecture, although unlayered architectures are fairly uncommon in practice when compared to layered network architectures. A strong security framework is essential to the reliable and efficient functioning of any network, just like Barry described earlier. The aim of the security framework is to protect the data and network applications from malicious adversaries who are capable of unauthorized access and modification of the data. The basic step in any security framework is to formulate a well-defined set of security objectives. These objectives determine what is to be protected in the network and to what extent the data and applications are to be protected. The objectives are generally defined by choosing a security model, such as the CAA triad model, which was previously discussed by Barry. So once the security objectives are formulated, the next step is to implement them as a part of the network communication. So this is generally done by identifying a set of cryptographic protocols. We shorten them to crypto protocols. So these cryptographic protocols are identified by considering what threats are noted and addressed in the security objectives. And then once the cryptographic protocols are identified, the next step is to combine them with appropriate network communication protocols. And this final step is generally dependent on the network architecture. And the general consensus is that with this, with the appropriate combination of cryptographic protocols with communication protocols, a strong and secure network is obtained. Now, Barry will continue the presentation by describing how to protect a network from threats posed by adversaries that have quantum capabilities. Thank you.
Thanks, Shalini. So as I said at the beginning, Shalini is my PhD student, and she's done 99% of the work. And I'm glad you had a chance to hear a couple of slides from the student behind the ideas.
Thank you.
In this slide, I want to talk about the background related to defending from a quantum adversary. Now, so I'll just mention a few papers here. And the key point is that the way that we think about quantum information for protecting at the moment is we have a very well-defined protocol. And the purpose of this presentation is not to design protocols, but to figure out what's needed and how to fit them into a network. But let's go through what are the current protocols. On the left, you can see very recent, June 2020 publication from Reviews of Modern Physics by the group in China with collaborators. They're the ones that launched the quantum satellite, and they wrote a beautiful review article on secure quantum key distribution with realistic devices. So this is a review of the state of the art in 2020 of how keys are distributed. Now, distribution of keys is important, but it's one part of a secure quantum network. On the upper right, this is an almost 20-year-old article on authentication of quantum messages. On the lower right, you can see how to share a quantum secret. Those two, that's a 21-year-old article. And actually the one on the lower right, you can see was partly from Calgary. Those two articles are just highlighting to you that quantum key distribution is not the whole story. There are other protocols. And in the middle on the right, that article on post-quantum cryptography came out a couple of years ago in Nature. And that one is really addressing issues concerned with how to defend networks, communication against adversaries with quantum computers. So there's a lot going on. There's a wider range of protocols. Shalini and I feel that there's not enough protocols yet. So there is a need for other kinds of protocols that are suggested by considering the quantum network carefully. Shalini did a great job of talking about two networks in detail, the OSI model and the TCP/IP model, and then she mentioned another that those are layered, and she mentioned the flat version. This slide is now giving you background on the quantum networks, and you'll see how different current quantum network architectures are. On the upper left, that picture is from the company Evolution Q, which is a Canadian company that develops architecture. Their architecture is based on a European network, SECO-QC, that proposed a 4-layer network. And you can see that they have at the bottom, it's the QKD link layer. QKD is quantum key distribution. Then there's the QKD network layer on top, key management service, and then on top is the user layer. So whereas OSI had 7 layers, their development is a 4-layer system. And there are reasons for it. It relates to a lot of aspects why it's 4 layers. On the upper right, you can see again with the short DOI reference below it, this is an example of a 4-layer network, which has the physical link, network, and transport layers. And on the bottom is another 4-layer system. So you can see that the 3 quantum network architectures we identify at the moment are all 4 layers, not 7 layers. So it's interesting. I mean, we quantum scientists who are looking for how these quantum protocols are going to translate into network applications should be thinking carefully about the number of layers, the security thereof, why they're designed that way, what tasks they fulfill. But that's just giving you the background of where things are at. Now, let's talk about the security threats to these quantum networks. The warning that Shalini read to you points out that in the classical world, it's clear that security needs to be co-developed with quantum networks, not added later. And that's not done in the quantum world. So we think it's an important warning. This slide is just mentioning some major threats. So there's an archive paper that came out in May this year, Van Meter's group at Keio University in Japan. And this just mentions some threats. These are the ones we highlight as major threats. One of them can be malicious entanglement. So the entanglement you have is not the entanglement you want. There are side channel attacks. These are well studied in quantum key distribution. Fault injection, blinding detectors are examples. Out of system attacks that can be done by using degrees of freedom away from the system that's being used. And attacks to clock synchronization. So these are major threats that we don't make up. These are out of the literature and they need to be considered. So how do we go about doing it? Now we're starting to understand the threats. And so here I want to talk about our approach. And we have 4 stages in our approach. One is that we, bearing in mind the particular network that we want to deal with, we augment the classical network capabilities. These are the services provided by the network. We augment them by providing quantum functionality. By that, I mean that in the way that Shalini and I are thinking, we consider an existing network. So instead of working with the 4-layer network others propose, we consider what an existing network is, whatever it might be, that can be told to us. And then we consider the tasks, and then we work on the quantum functionality that's required. And one quantum functionality could be sending qubits coherently from one point to another. That would be coherent transport. And we call this a weak quantum network. Another one, which is a topic of current study, is entanglement generation. So the idea is that within the network, there might be a multi-partite entanglement. It could be pairwise entanglement. So every pair of nodes could share entanglement, or we could consider a multi-partite entangled state. And we just refer to networks that only require coherent channels as weak quantum networks, and networks that involve entanglement, we just call that strong quantum networks. As entanglement's harder than coherent transport, typically. Okay, so we consider a network and then we augment it by adding quantum functionality to it for some purpose. The purpose could be just communication that's secure against a quantum computer. Once we figure out what the quantum functions are, we then assign them to layers. Now, a layered network could be sufficient. We can take a layered network like OSI, and then we simply use that network structure and figure out what the quantum functions are and assign those to existing layers. If the network is not layered, a flat network, then we consider typically how to add layers to employ quantum functions. So our approach would be to, even an unlayered network, we would add layers to enable quantum functions. The layers provide a convenience to be able to do careful security analysis. Once we do that, then we have our network, we've incorporated quantum functionality and assigned it to the layers. The next step in our approach is to formulate the security objectives. And for this, we first need to assess the threats. And I've gone through threats: malicious attacks, malicious entanglement, sabotage, the various things that I've discussed in the previous slide. And so once we figure out what the security threats are and the security model context, which for our purposes is the CIA triad, then we formulate the network security objectives. So what exactly does the network have to do to perform the tasks at hand, whether it's clock synchronization or distributed quantum computing on the cloud or whatever. The network security objectives are then clearly articulated. And then once that's done, then we have to establish the protocols. And the protocols might exist. We can possibly use quantum key distribution or post-quantum crypto methods, let's say a lattice-based scheme, or we might consider quantum versions of protocols that haven't yet been developed. So we might consider, say, proof of work protocols and how to extend those. So once we figure out the objectives, then we identify the protocols that are needed. And good news for us scientists, a lot of the protocols we needed aren't developed. So it sets down a work plan for what needs to be developed to address those needs. Okay, so the main promise that we made, their main claim is that we've developed this framework. What does the framework look like? Well, we're suggesting a 5-layer quantum network model. So I showed you in the background that the existing versions are 4-layered. We think 5 layers is needed minimum to be able to accommodate the security objectives. In this table, we have we've listed aspects of our model. In black, these are existing concepts. So we're just taking from the literature. Now, in the literature, some of these points that we're raising are not yet accommodated into a network model. We've done that. So whatever you see is black is taken from the literature, and the right column, which is assigning security threats to layers, that's new, but shown in black. Anything that's in red are things that we have added to the literature, and anything in blue, there's only one item, is something that's in the literature, but we modify accordingly. And for the background, there are the references I've given before. You can see the short DOIs in the first bullet point. So again, you go to doi.org, you type that in, and you'll see the papers. Okay, so let's start at the bottom. So there's a physical layer, and there's no change to what exists in the literature. And I'll just talk about the functions and the quantum. So the functions that would exist in a weak quantum network and a strong quantum network. So the second column are the functions we need if it's a weak quantum network that involves coherent transmission of qubits. The third column is for the strong quantum network, and that's the one that makes use of entanglement. So you can see that we're doing a 5-layered quantum network model, but we're differentiating the functionality between the weak and the strong quantum network versions. And so in the physical layer for the weak quantum network, it's point-to-point delivery of quantum state. That's coherent quantum channels. For the strong quantum network, it's generating point-to-point entanglement. So that requires entanglement. That's all done at the physical layer. And that's studied well. And this is something that physicists like because it's a way of developing better quantum information and assuming it's needed at the physical layer. Now let's go up to the link layer. So the link layer is about controlling physical transmission of quantum data, but an additional quantum functionality is to be able to support the point-to-point crypto protocols and to be able to perform quantum demolition measurements, i.e. see the photon and destroy it, to ensure the data delivery. Well, those are quantum measurement and aspects related to supporting quantum crypto, and these need to be assigned at the link layer. This is why we like to add layers to consider how a quantum network would work. For the strong quantum network, the reliable point-to-point entanglement generation has been discussed, and that's a link layer protocol, but assigning addresses to qubits that are involved with point-to-point entanglement, this also needs to be in the link layer, and this is a novel aspect of what we're talking about. When we go to the network layer, that's the third one going upward, actually third one going up and down. That network, so in the weak quantum network, this has been considered, it's about routing and about assigning address to devices in a network. The generating end-to-end entanglement, we modified a bit, and that's a network layer one. And then the next one up is the transport. And for the transport layer, for the weak quantum network, we're saying that we need to incorporate end-to-end delivery of quantum data, end-to-end crypto protocols, and the key management for applications. Has to be in the transport layer. In the strong quantum network, the supporting end-to-end quantum teleportation, which is one way, like using entanglement to teleport qubits is one way to proceed, but we also need to be incorporating assigning the address to terminal qubits. Just to give you some context, most work in labs to date is about 2 points. So these kinds of things are trivial in existing networks, but a multi-party network requires consideration of these points. And then the top layer that we've added and is not in the literature is the application layer. For the weak quantum network, it's about generating the quantum data for transmission, manipulating the data, and measuring. In the strong quantum network, it's about assigning the address for application qubits. And in the last column, which I won't go through in detail, these are the security threats that we've taken from the literature. And as I said earlier, we take existing security threats from the literature, but we assign them to the various layers, because in the security objective establishment, we don't just need to know what the security threats are, we need to figure out which layer they pertain to, so we're able to develop protocols that will mitigate these issues. And some of them just mentioned to you, in the network layer, you can see network sniffing. So network sniffing is just about things like detecting network traffic, properties that are going on inside the network and sniffing them out. The malicious entanglement I mentioned before, we regard as a threat that needs to be accommodated at the link layer. So I hope this slide conveys to you the framework that we're using. And so rather than us presenting the solution to a particular problem, you get the idea that we're sorting out what is done and what needs to be done. And so our project is less about solving quantum problems and more about identifying quantum problems that need to be solved. So in a sense, we're not doing the homework, we're creating homework through this slide. And my final slide is just the conclusions, the take-home message. So this is what I hope you take away from the talk. So I'll first talk about what we've achieved, and then I'll talk about the homework. This is what we need to do. And we as collective, I'm happy to talk to anybody here about what needs to be done. So what have we achieved? Well, the achievement that we're most proud of is this framework that is represented by the table in the previous slide. We've developed a framework for layered quantum networks. Using that, we've gone beyond the 4-layer network in the literature to a 5-layer network. the 5-layer network is very clear on the applications, which we need to be clear to start assessing security threats. And we've sorted out the security threats layer by layer. So that's the nature of our framework. Another important achievement that we think is that we're incorporating classical and quantum communication in the network on par. That means that we're dealing with communication as an aspect of the network. And then whether it's classical or quantum needs to be treated in the network at the same level, but of course the protocols will differ. The third achievement that we think is significant is, and this goes from that RFC warning from the network working group, the one that Shalini read out, is that contrary to what's taking place in the field right now. So I want to be clear. I think I admire a lot the work that's going on. We have outstanding work going on these days on developing quantum networks, both experimentally and theoretical frameworks. We have excellent work going on with relation to cybersecurity that protects against quantum adversaries. The issue that we think is not developed enough, and where we're stepping in, is that they need to be co-developed. So we're establishing the framework so we're clear on the security objectives, and then that is incorporated directly in the network at stage 1. And we think our 5-layer network is capable of doing that. And the fourth point that is the take-home message is the importance of the application layer. That new layer that we've introduced in our 5-layer model is not just another layer to consider, but it's prioritized in the sense that that needs to be considered carefully. And quantum resources are incorporated, but the application layer needs to be clear to figure out the quantum resources required. So those are the 4 key points that we would like you to remember after this talk. What's left to do? Well, many things are left to do, but this is kind of just a broad stroke explanation of what needs to be done. The first point is, now that we've prioritized the application layer, we need to analyze these applications carefully and understand what network and what security built in the network are needed to take place. The two that come to mind as priorities, well, one is the quantum key distribution network, and this is a national and international priority in various places. You know, I've mentioned China's launch of a quantum satellite. They have now more than 1,000 kilometers of ground-based quantum key distribution. So China, I would argue, I think everybody would agree, is the leader in developing quantum key distribution networks, but they're not the only ones doing it. Other places are doing it. Here in Canada, we have emphasis on quantum key distribution networks, and we're strategizing for that. Places like Singapore, Russia, et cetera, are developing these quantum key distribution networks. They're creating the pieces that are needed for ultimate quantum networks, and we need to think more about how to incorporate all the deal with security threats. And this is being done, but our framework can add a lot of clarity to it. And the other one that I mentioned is the synchronized quantum clocks. This is an exciting area. It's extremely challenging, so I don't promise that it's going to work to the level that it would develop outstanding GPS systems, say, but it is a hot topic. And in science, we like the high risk, high reward type of research. So synchronized quantum clocks are a challenging topic, but now is the time, as we think about the networks, get the network right for a synchronized quantum clock. You know, if we develop these fantastic quantum clocks that would serve as GPS, very accurate GPS systems, what if a malicious party changes our clock, or if the clock, we get a denial of service attack, so our clock doesn't work? The dependence we have is extremely important. There's quantum protocols that are needed, and we have to deal with those. And the final piece of homework is to develop appropriate quantum security protocols. So we think of things like quantum key distribution. We think of, I've mentioned to you, authentication, secret sharing, but there are many other potential protocols. I don't list them here, but I can tell you that what we do in my group is we just go through the protocols that are used in classical networks, and then we think about what the quantum, is the existing protocol in a network sufficient to guarantee the security in the context of the CIA triad? And if not, can it be made, can it be adapted to become a quantum protocol? And if not, what would be the quantum protocol that would replace it? So that's the homework. I appreciate the chance to give. As I said at the beginning, it's the first time we're presenting the work. So yeah, I'm sharing with you very new work, not written up. And it's a kind of a roadmap for where to go on this. And I hope I've left plenty of time for questions. Thanks for letting me.
Boris, thank you very much for this very exciting talk, this presentation of very fresh and new results. In this framework, I want to ask you questions. What is the technical level of quantum communication devices in Canada at the moment?
What is the technical level of quantum communication devices in Canada at the moment? Okay.
Yeah, do you have real devices providing quantum communication on par with classical communication?
Well, we have, so here in Calgary, there's a couple of big emphases which are on the development stage. One is we do a lot of work that we think is world leading on quantum memory. So it's really being able to store the quantum information and release it on demand is important. We're developing in that. So that's an enabling technology. We also have what's known as transduction or hybridization. It's converting quantum information from one form to the other. So the communicated quantum information would be photons. We can put them into diamond, store it in diamond, or we can store it in, convert it with nanomechanical structures. So there's that. We have demonstrated real world quantum communications. So over a 7-kilometer distance, it's 11 kilometers of fiber through commercial quantum networks, commercial fiber networks that so we just lease optical fiber from a company, and we've demonstrated secure quantum communication in that way. We do have the plan soon to set up a ground station to communicate with quantum satellites. So that's in Calgary. In Waterloo, they have a ground station for communication with a quantum satellite, and they're leading the effort for Canada to launch a quantum satellite. So we have preliminary funding. I'm not part of that. I'm connected a little bit, but it's other people in Canada who've developed technology that would go onto the quantum satellite that Canada plans to launch. There is an intention to set up another ground station at another city in Canada. In Waterloo, they've done free space quantum communication, so building to building within the city. We have companies like Evolution Q that I mentioned earlier. So Evolution Q is a company in Waterloo that's focused on threat assessments, on architecture and other things. And so, and then on the photonics side, we have developments in photonics that are relevant. And finally, in Ottawa, at the University of Ottawa, the group with Bob Boyd and Ebrahim Karimi is developing light with orbital angular momentum. So instead of sending, like we normally think of light 2-level with polarization or early late or something like that, and they're working on higher dimensions. So with orbital angular momentum, we can make 3 or 4 or 5, whatever, multiple levels, and they're studying quantum communication with that. So there's more going on, but that gives you a picture.
Any other questions, please? You can write a message or ask just by raising hand. There's one question. How realistic do you find the idea of creating a hack-proof network?
Okay.
Would it make sense to work on tools to detect possible infiltrations at the same time?
Right. Okay. Thanks. Yeah. So, well, first of all, with a hack-proof network, we know the internet's been around a long time and it's still hacked. And in fact, a lot of the compromises to the security are by human beings, phishing attacks and so on. So I would say that I think theoretically a true hack-proof network, even using quantum resources, is not ever going to be viable. Second, as long as human beings are involved, humans can be tricked or corrupted. So there's always that problem. This then speaks to what we're developing, which is the threat assessment. So the idea is that we have to have a model of the network and a model of what the threats are, and then the security objectives. And so we can never prove that anything is completely secure, but if we model the threats and devise the protocols to protect against those threats, then we're on the right track to delivering security with risk mitigation, which is what they do in networks. The key point of our work is not to deny all hacks, but really to, a key point is to protect against adversaries with quantum resources. So currently with our networks and the threat models, we assume that the hackers, the malicious parties, are not quantum enabled. They do not know or are able to use quantum physics behind their technology. And what needs to be done is to say the adversary who attacks the system can use quantum resources for all aspects. So we're not trying to devise a hack-proof system, but we are trying to elevate the threat assessment and the security objectives to protect against adversaries with quantum capability. I hope that clarifies things.
Any other questions, please? So we have a question from Zeki Seskir. Have you performed any simulation on the effect of adding this additional layer to the key rates?
Good question. No, we have not. So no, I've done work, quite a bit of work on simulating key rates under realistic conditions. So over the time, I've been working with people on these simulations. You might, I'll give you an example. There's a article that we had out. As you heard in the introduction, one of my positions is with the Raman Research Institute in Bangalore in India. And there I worked with the team. So India is developing its secure quantum communication capability. And I worked with the team there. We have an article out 2-3 months ago in Physical Review Applied. And it's a long title, but the first part is QKD Sim. So in QKD Sim, we've developed a software for simulating the key distribution, taking into account a lot of different aspects under realistic conditions. And that will deliver rates. So that's kind of the basis. But then being able to simulate for a proper network is still in the future. So part of this QKD Sim development that I've worked with at the team at the Raman Research Institute sets proper software principles that we're able to build on in order to do proper simulation of the network. So the simulations aren't that easy. It's not like we can just go and write code to do everything. There's a set of stages that we have to develop properly to be able to incorporate all this. So that's a homework issue. I like the question a lot. It's something that needs to be done, and it's not easy to do.
Other questions, please? So, if no questions, Barry, maybe we can stop here. What do you think?
Yeah, I think it's right. It's almost an hour, and I take that there are very few questions because the message might be clear.
Yeah. Thank you very much for this talk once again. Please note that we look very forward for your visit to our institute to take participation in our quantum school as soon as this pandemic settles away.
Thank you very much.
Very, very nice to discuss these very hot and exciting topics with you face to face. Yeah.
Thank you. Appreciate it.
So let us hope and wait to meet in person in future. So thanks.
Thank you.
Thank you.
Salini, thank you very much.
Thank you very much.
Yeah.